Morning, everyone. I'd like to welcome you to this innovation session. We chose the word innovation because we think this session is going to be one of those that has interesting things. And to kick us off, we will have Dhruv from Huawei coming to give us the IETF roundup. Dhruv?
Wrong presentation. IETF roundup. The one you had previously was right, yeah. Yeah. Hi, everyone. Let me move this here, it's much easier. Yeah, hi, everyone. I'm going to give you a quick roundup of what are the latest things that are happening at the IETF. Just before I start, can we have a hands up of how many folks know what IETF is and what they do? Okay, we still have few hands down, so I have a slide that will give us a quick introduction of what IETF is all about. So, before we do that, I'm Dhruv, my pronouns are they and them, and at IETF, I'm on the Internet Architecture Board, which is IAB. I chair a couple of working groups like Path Computation Element, Education and Outreach Directorate. I'm also the IAB Outreach Coordinator, and in that role, I'm coming and outreaching to the Apricot community and suggesting what are the interesting things that are happening in IETF and how we can come and participate. The mission of IETF is something that we can all agree with. It's here to make sure that the internet works better. We produce high quality documents, the RFCs, which are easy to implement, easy to understand, and gives the best current practices in running our global internet. We all can agree that standardization is very important. We are all operators. We all need to interoperate, and that's where technical standards come into play. We all have networks which are they don't look alike, but they still need to connect to each other, and still the global internet needs to function, and that's where the IETF standards come in play. The unique things about IETF standards is they are freely available. Anybody can download, no membership, no login. All our documents are easy available. Not just the final output, but you could also see every draft version, every meeting minutes, every time a particular topic was discussed. Everything is freely available for completely free. Anybody can come and participate easily. Of course, running a meeting costs you things, so if you are attending, there is a cost involved. Remote participation is very good these days, and people can come in and participate, ask questions. Remote participation also is charged, but you can easily ask for a fee waiver if meeting cost is a problem. So come and participate, it's completely open, easy to participate in, no membership, no approvals. Come. Another thing that I wanted to highlight was that we work on something called as a rough consensus, which is a very unique thing in a standards development case. There is no voting. It's the chairs that call whether the group has discussed a particular problem enough, and there is enough consensus and running code to back it up, and then it gets into the last call and processes and finally published as RFC. We believe in openness, we believe in innovation. That's why you will see a lot of new work that is happening at IETF that I will cover in the coming slides. So, some idea of what are the recent things that we have done in past. There's a lot of development in the security area, a lot of updates like TLS 1.3, HTTP 3, things like that. So that security and privacy is built into our protocols from start. Automating network management, a lot of work on YANG, NetConf, RESTConf. Those things are all about how we can run our networks better. New transport protocols like QUIC. We had a discussions earlier when Jeff was giving an introduction of the encrypted traffic in QUIC that we are seeing. That's also a technology that got standardized at IETF. IoT, a lot of work related to that. Some of the major success that we could see, WebRTC, TLS 1.3, MLS, which stands for Messaging Layer Protocol, that's also a good one, and QUIC. WebRTC, in fact, during the COVID times, we all realized that how internet played such an important role, and the Zoom meetings and the WebExes and Teams and everything relies on this IETF protocol, WebRTC, that was developed at the IETF itself, which enabled so much of the work being done on our internet. At IETF, it's not just standards and RFCs. There's a hackathon event that we do because we do believe in running code. What is most important is to see the results of how the protocols which we are designing, how would they function in reality. So hackathons are interesting work to participate at IETF, especially for folks who are not as interested in writing the standards, but are more interested in development or running the networks. There are, in fact, some operator-led projects at hackathons related to BMP, related to IPFix, Yang and Kafka integration. These were very interesting operator-led hackathon that were happening at IETF. So I wanted to say that that is also for some folks who are interested in hacking side in this room, they can come and participate at the IETF hackathon as well, which is a very good entry point into IETF. Some of now updates of recent things that happened. Like any other organization, we love to reorganize ourselves once in a while. So we have a new IETF area. And this area is web and internet transport. We do realize that these two things were the world is changing with HTTP, with QUIC, with close relationship between HTTP3, that it's important that we club these two technology, web and transport, internet transport closer together. And that's the reorganization that we did. And the transport area, which was called transport and services, that is closing down. And we have a combined WIT area inside the IETF. This is going to be the organization structure. As you know, that all the works gets done at the working group level. That's the most important one. In the middle, you will see the areas. So there is application, internet, ops and management, routing, security, and the new one, which we see WIT. The things that you see in red are the new leadership. So we had our NOMCOM process via which we select our leadership. So there are some new area directors that you are seeing on this page. We have a new IETF chair as well. There was members in the IAB where I belong, which is on the top. There's a research arm of IETF, which is IRTF. A lot of interesting research groups are discussing things like even network management research group. What's the future of things like digital map, network maps, those things, role of AI in network management. So those interesting topics are also being discussed in IRTF as well. Another thing that I want to highlight is we have the RFC editor function, which is sort of outside, mainly because RFCs are not just from IETF, it's IAB stream, it's much other streams can publish. Independent stream can also publish RFC, so RFC editor sits on the edge. Sorry. This is how, in the layered diagram, we would look at IETF work, sort of internet being at the bottom layer, where we have things like 6man, which is the IPv6 maintenance group, a lot of things related to DNS, NTP, the internet level protocol, which are the infrastructure for our network. Over that, we get into routing, where you have LSR, which does OSPF and ISIS. We have BGP and IDR, MPLS working group, things which I do, which is path computation element. Again, SDN-related protocols, which are between controllers and network devices, those all come into this area. Over that, we have web and internet transport, the new one. You have things like HTTP, UDP, QUIC, congestion control, all those things belonging in WIT area. And then on top, we have WebRTC, SIP, RTP, email core, things which are application protocols and real-time protocols that belong on top. And on the side, always there is going to be operation and management irrespective of which layer your protocol belongs in. And similarly, security is important everywhere. So that's why the two pillars, the two vertical things that you see at the end, those are all IETF work that you will see. So based on which area you are interested in, there is a lot of work that is happening at IETF that might interest you. Now, my main job here is to give you a quick update of what happened at IETF 118, which was in Prague. And just a disclaimer, this is not an official report. This is just my collection of things that I think you guys would be interested to know about. And BOFs are sessions which brings in new work into the ITF, so they are actually very important. And these also needs operator inputs the most, because we need to decide whether ITF should really charter this work or not. So I wanted to highlight these things for this community. This is the new work that is coming in. DULT, which stands for Detecting Unwanted Location Tracker. This is all like in media, you must have heard of reports where air tags and Google tags were being used to track people, especially in a relationship where there were abuse involved. And there were lots of news stories related to that. So both Google, Apple, and other vendors came together to the ITF that we want to standardize a standard way to detect unwanted location tracking. And this work already this was the second BOF. We had a pretty good consensus in the room that this should be chartered. It belongs in ITF, even though the boundary is a little bit tricky because it does rely on Bluetooth a lot. But there is enough things in terms of how we are detecting and notifying, which is over the internet. And that's where the ITF has the right set of people in the room which can help standardizing this work. So most likely this will go on and become a new working group. Then these days, identity is a really important topic at ITF. So we had two topics which were identity related. One was digital credentials, again coming in from a lot of regulations at EU and other places where we want to standardize how to have digital credentials that can interoperate across things. Because usually we see this limited in one walled garden, but not working interoperability everywhere. So SPICE is that new area in security where they are evaluating, is this something that the ITF can do? And there is already a lot of existing technology here as well. So again, bringing them together, bringing a consensus that how we can have one standardized way, even when it is reusing things which might be already well established in the industry. Another interesting one is workload identity. So moving away from a user identity to an identity of workload, especially when we want to move things around in a computational world, moving from one cloud platform to another, how to interoperate the identity part easily. That's where the WISME, which is workload identity in multi-system environment, comes into play. So these were the three interesting BOFs. Pretty good discussions. They are not yet chartered. They are at the end of the process where the ISG will make decision whether there is consensus in the ITF to charter this work or not. Moving on to things which are chartered now. So lots of development. This already got discussed in the community, and these are our latest set of working group. One for this community, which would be very useful to see, is network management operations. Specifically asking operator community to come in and tell us what are the issues you are facing in running the network management protocol itself. Yes, we standardize NetConf, we have RESTConf, we have YANG, but when you actually are running this in your large-scale network, how are these operations performing? What are the missing gaps that we can come in, again get standardized either in an update of a YANG model or a YANG language, or whether a new feature in NetConf or RESTConf is needed to support this. Very operator-focused working group inside the ops area. The current thing that they have highlighted, again, this work started coming from Hackathon, where people were working on NetConf, YANG push, and Kafka, how they can be integrated in the network management system. So that has become now a chartered item inside the NMOP working group, where they will come up with what they have done, how the integration was, where the integration is difficult to do, and what could be the enhancement in the protocol that can be done to make this integration run smooth, so which is very important topic. Again, incident management, anomaly detection, what are the best practices, what can be standardized, those discussions will happen. And in general, any issue related to network management protocol, this is the new working group to discuss. So again, I'm sure a lot of folks in the room who are actually running network management systems, are using modeling, are doing things like Kafka, would be interested in this working group. I will quickly go over some of the other recent working groups. CATS, which stands for Computing Aware Traffic Steering. The idea here is in your network, the same service can be provided at multiple endpoints. Instead of just looking what is my network behavior at that time, and based on that, I select which endpoint I should direct the service to. I look at both the compute metric and the network metric, optimizing both, and then deciding where to steer my traffic. That's what CATS is standardizing. So they would have work on metrics, that how do we define those metrics, how we advertise those metrics, and then relying on things like segment routing or whatever the underlay tunneling technology that you will use to still steer the traffic in the right place. But they are more focusing on the decision-making aspect of how we make those decisions, which metric we take into consideration, things like that. Another good one, which I think this community is interested in, is network inventory. We all do that. Again, focusing on a common YANG model that we could develop for network inventory, which takes care of both physical, virtualized things as well, and how we can make it work. So full life cycle management is part of this working group charter. Time variant routing, which is things like in your routing systems, there are periodic things that might happen. Periodically, a link may go down. For instance, if you think about Leo systems, this might be useful. Or a system in which at a particular schedule, my topology changes. If I know about these predicted changes, how can my routing system work in an efficient manner, taking timing as a constraint while I'm doing my routing? Quite interesting. Key trans, focusing on identity to public key binding, again, very security focused group. Congestion control working group, they are chartered to update an old RFC, which is RFC 5033, which is a BCP, which looks at new congestion control algorithms, and things have changed in the world since it is published. So again, a working group is chartered. Come, let's discuss, get in consensus, and bring out new best practices and guidelines in our system. Folks who do a lot of implementation and testing already might know about BPF, which was initially, the thing was, it was mainly for Linux systems. But now, since the BPF can be done for Microsoft, it is being implemented on line cards, it's important that it gets standardized. It doesn't live inside the Linux code, but it's important we follow a standard mechanism to document this. And they have chosen to bring that work to ITF, which is a very unique set of a working group where we have never done exactly something like this. But again, ITF is also sort of experimenting and expanding on what all new work that we can take as our industry is changing. Structured email, again, a very simple idea, which I think we already are using. Calendar invites and things like that that we get from Google, for instance, are very structured so that a machine can parse them and get enough information out from it in a structured way. So a lot of people are working together on how we can standardize some of these features, which we are already seeing out there in some of the mail providers already. So this was this thing. I have 10 minutes, so I'm going to just try and speak a little and focus only on the key points now. V6 Ops, very interesting work. There is a Happy Eyeball version 3, which is being discussed. This work is, it's not just about picking V4 plus and V6, but looking at security, looking at what kind of other parameters that I can use for selection. So it's a new version beyond basic IP. So that's why this being discussed quite heavily in the next ITF, and hopefully we will make a decision on where this work belongs. In fact, one of the things that I want to highlight is APNIC Foundation and ISIF Asia grantee, which is an NITK institute. These students went to V6 Ops and talked about, within our students' network, within our campus network, how we are working on V6 deployment, which is very interesting, and it's in fact funded from APNIC and ISIF Asia, so we are very thankful for this work can happen at ITF as well. There is GROW, 6man, SR remains very interesting, and even in this program, you could see there are lots of SR-related topics, so that's continued to grow at ITF. IPG is a separate meeting that in ITF we have on Sunday, which is completely operator-focused. Again, we are asking for more and more inputs from the operator community, and there are very good presentations. There was a presentation on packet discard recording, metadata annotation, performance of Starlink. So lots of good, very ops-focused topics that get discussed even at the ITF meeting. So you will find a lot of interesting things, not just the protocol bits and wires at ITF. There is side meetings at ITF, so you can just bring in any topic that you think where there is a community for discussion. AI for DC, which is a hot topic even here at our program that is being discussed. Yang Kafka integration, digital map, incident management, lots of different things that you will see what the operator community is interested in is being discussed at ITF. Now in the last part, I will quickly go over the upcoming ITF, which is ITF 119. This is happening in Brisbane next month. And thank you, APNEC, for being the local host for this meeting. This is from 16 to 22nd March at Brisbane Convention Center. So even if folks who cannot make it to Brisbane, the time zone would be very much aligned. So come and participate remotely, join, ask questions. Remote participation is default. Hybrid meetings are default at ITF now, and enough questions. You can have a pretty good discussion remotely as well. So come and join us live. There are some BOFs, which is again a new working group, which is being proposed at ITF 119. This will be discussed for the very first time, and some of them are very interesting topics. The DELEG, which stands for New DNS Delegation, it's looking for better delegation method for parent zone and adding more capabilities such as aliasing delegations with other domain names, DNSSEC management, which encrypted protocol to pick, things like that. So this is a new interesting work. There was a blog at APNEC as well, in APNEC blog that gives a good history of what's going to be discussed in this DELEG, because some discussion already started in DNS OP working group, but now they are discussing whether this needs to be chartered as an individual item rather than only be done inside DNS OP because it has bigger impact. SRv6 ops. This is saying that, like, with SRv6 being deployed more operators bringing in their operational issues that they are facing and which they think needs to be solved before SRv6 gets deployed more. So things like that are being discussed. People have talked about good address management, how we should allocate SRv6 sets, what are the best practices. So we will decide whether there needs to be a separate BOF focus on SRv6 or whether that work already belongs in some other working group. So that would be the main discussion that will happen at this BOF. Again, a very important topic, going back to Jeff's presentation when he was mentioning about everything being encrypted and networking not having a control. Well, there is a proposal. What if a network can signal things to clients in a cryptographically secure way? That's where security communicating network properties comes in. They had a couple of side meetings before, and now they are seeing that whether we can form a BOF and whether this is ready for prime time. Their focus initially is very much on QUIC and video bitrate. They are focusing on video traffic. They are focusing on QUIC to start with. But if this gets go, I have a feeling that this could see applicability in a lot more use cases because this is very important. As Jeff also highlighted, like we are losing our ability to look into a network and be able to make decisions. So again, while keeping the security and privacy alive, can I still signal enough things to my clients itself so that they can make the right decision? That's the approach this group is taking. There is an all dispatch, where dispatch is a way where ITF decides that how we should progress a particular piece of work, whether it should have a BOF, whether it belongs in an existing working group, or whether ITF is not interested in it all. That's what dispatch does. This time, there's an all dispatch where we are merging all the dispatch groups and having one session, 3-hour session, marathon session on deciding this at the start on Monday. NMOPs, which I talked about, will meet for the very first time. And some of the previous BOFs, which I've talked about, DULT, SPICE, and WISME, they are most likely to meet for the very first time as a chartered working group. Hopefully that happens. There's a blog at the end, which if you're new, what are the sessions that might be of interest? So do check that out. These are my final set of slides. So hackathon as I suggested, is a good way to participate. There's a technology deep dive, which is focusing on BGP. So a very good introduction from on BGP, and also BGP as a dump truck. Many people worry that we are putting too much things into BGP. Everything is being carried over BGP. So a session which delves into that. How did it come to be? What will be the breaking point? Where do we stop? Things like that. So it's pretty good discussion. So if you are interested in that topic. The final thing that I want to talk about is IPG will continue. There is new ITF leadership. IAB Open, which I'm part of. This time we have invited Thread Group, which is very IoT focused, to talk about what ITF standards, the role they play. Encryption laws in Australia. So again, policy area is also very important. So we have invited folks who are working in this area to come and talk to the ITF, explain what's happening in Australia since we are meeting there. IRTF Open, again, has a very good research paper being presented on anomaly detection. Again, something which is useful. Full agenda is out. Do check it out, and hope you guys can participate. My final slide is just a sort of a pitch, folks, to say that why network operators need to participate. And it's like it's for the vendors or researchers to go to, but like, why do I need to go there? These are just my ideas of why we think like, you should participate. You will learn about new internet protocols and extension. There are a lot of things which are very operator focused. So even if you don't care about TLVs and bits on flags, there are enough things in IETF agenda that you will find where your inputs are needed and very, very valuable. Then why should you care? Where we ask the questions are, where you have a very specific answer is, are these real problems that impact you? Are these real network requirements? What's missing? Are they in sync with your actual reality? Would you be able to actually deploy this? Would you be able to transition into this? Does the protocol takes care of enough things to help you troubleshoot when things goes wrong? This is where your inputs come matter a lot. So ITF especially needs to hear your voice. Tell us your requirements. Don't let vendors and researchers do that. We want to hear directly from you. Provide insights, and just don't shy away from using your operator card. We are doing this because you could deploy these technologies. And if you are not able to, if you have issues, we are all ears. Use your operator card, go to the mic, and tell us where we are going wrong. Some more tips to participate. And since I'm almost on time, I'll quickly say thank you and would rather have any questions from the room.
Thanks, Dhruv. Any questions for Dhruv? I think I have one, maybe just for the benefit of the room. So obviously you are, what's the title again? Chief Standards Architect at Huawei. So as a Chief Standards Architect, this is all you look after, pretty much. And what does that entail? Like if a company employed you specifically for that, what does that actually mean? So
my ITF journey started with as an implementer. So I worked in Bangalore office of Huawei. I was implementing MPLS VPN, implementing things like when there were still drafts, Martini and Campella, so I'm telling my age. And that's how I got into this thing. And during that time, you had new ideas of, the protocol could be extended to solve these issues in this way. That's how I started my participation in ITF as an implementer, looking at more on hackathon side in this. But slowly and slowly, now I moved to a pure standards team, where we are looking at multiple things. There is an industry strategy that we set up within Huawei, that how we should look at standards and how standards can help us and we can help standards. So since I am on the IAB, a lot of times my company give up my time to work on the IAB, to support me on various issues that we take for the IAB, which has no direct impact for the company itself. But within the within my company, my role would be to look at the strategy, like which working group we should focus on, what should be a strategy, who should we cooperate with, find the right partners so that we can push the technology that we care about and help the industry. Also working with industry cooperation, working with university partners and other things on just making sure that we use the internet standards in the right way within our industry. So that would be the overall answer.
Fantastic. Yeah, one question.
Hi, Dhruv. I'm Vaibhav from Hasso-Plattner Institute in Germany. Thanks a lot for the talk. This was very good overview on understanding the IETF. I have been not so much active in the IETF in the past couple of years. I was a bit surprised when one of the slides that one of the areas, the web and the transport area is merging. And so that's leading me to the question. I guess it's not a secret that content delivery networks drive standardization at the IETF, and CDNs largely believe that the internet is the web and the web is the internet. And so does this merger actually indicate that most of the transport protocol work will now be driven towards building a better web and not anything else? And like, could you share a bit about how did this discussion actually end up into merging this area?
I would not read this much into it. I'll tell you why. Because the way IETF works is very bottom up. Things are going to be done at the working group level. So working group has a charter and they have to make a consensus at that working group. The only thing which made it matters is where do you park this working group? So we have an area under which you park a working group. So there is no working group level decision or area level decision. Either the decision happen at the working group level, which has a charter, or at the whole IETF level. So working group last call, IETF last call. Having an area and where you park doesn't change the actual output of the IETF. Your RFC would remain the same, whether you took it in the previous transport area or whether you're going to take it in web and transport area. It usually what happens is it's very much dependent upon the load that we are going to put on the personnel, the people that we have selected to be the area director of those groups. Since these set of groups now work much more closely, like we cannot have an HTTP person without having a transport person in the same room because those decisions cannot be made in silos. There is a good level of interaction that happens in these groups. So the main reason is for the area directors and for ease of arranging meetings, let's club them together. That's not going to change into the final consensus on the document itself. Hope I answered that well.
Yeah, fantastic. Okay. Thank you so much, Dhruv.
I'm here all week. If anybody has any questions about IETF, participate in IETF, having difficulty writing a draft, not understanding our tools, please feel free to contact me. I'm here all week. Thank you.
Thanks, Dhruv. Next up, we'll have Thomas Weibel from Flex talking about coherent optical transceivers.
Thank you very much, Mark. Hello, everybody. Yeah, my name is Thomas Weibel, I'm co-founder and CTO at Flex Optics. And the slides are going to be too fast now. So it's a really exciting topic, and I'm going to present it today to you because I think it's going to be a game changer in optical transmission in the next couple of years. And it started now. So where are we coming from? In the past, some of you might know transport systems around the place, especially for DWDM networks, long haul or metro transmission, or even subsea cabling systems. There is a DSP, a digital signal processor on that card. It is produced in some technique. Here is an example in 28 nanometers. And it transports the traffic from A to B. Now, in today, we take the same technique basically, but we shrink it down to a tiny, tiny chip. The DSP itself is now produced in 7 or 5 nanometer technique, and it got really small, and we were able to put it on a pluggable transceiver, and that's pretty amazing actually. So since the speed of 400 gigabit, we got this technology now, and it's available. And this talk is more about the innards now, so I will cover a little bit theory, not too much, but it's important to understand the technology. And then later on, I show you also how we implemented it together with a customer of us with its gear, and how especially we did the troubleshooting, because there are new parameters which you need to take in consideration. So let's first of all start where we're coming from. A typical transceiver 10 gig LR, which you are using in your lab or in your network, is based on direct detection transceivers. So what you can see here is a rectangle shape, up and down. You have two states, 1 and 0. and basically you encode 1 bit per symbol there. At the receiver side, it pretty much looks like a sinus curve, so it's a little bit distorted. The signal is not proper rectangle shape, but it's very easy for the receiver to detect the 0 and the 1. Now, what we did in the past, we just increased the speed. So that's what we do now. We're going to increase the speed, we increase the frequency basically, but on the receiver side, it's going to be a little bit more difficult for the receiver to detect. And finally, if we do it even worse, and it's even harder for you guys to see the slides now, and I help you a little bit, I do it like this. So if we increase the frequency very much, for the receiver it's really hard to distinguish between a 0 and 1. So we need a different technology to differentiate 0 and 1s, and especially for the receiver. So the good thing about light is it has not only the frequency part, so we got also phase and amplitude, and so far we haven't used it, and that's what we're going to change now. So phase and amplitude and polarization, sorry. And the polarization part is, I think, very easy to explain with either your privacy screen on your laptop, where certain the angles are filled out, or sunglasses, for example. And the same technique is going to be used in optical transceivers now. And to give you a rough idea, we did a MATLAB simulation of a signal on 2 polarized directions, so on the x-axis and on the y-plane. And when I start this now, so that's how the signal looked on the x-axis. And when we combine it now together, so we also need the y-plane as well. And now when we combine them, traversing on our fiber itself, combine both polarizations, the signal actually looks like this 3-dimensional something. And that's what the receiver needs to detect and to separate between the two polarizations. But beside polarization, I also mentioned we do have amplitude and phase, so we haven't covered that yet. And there, the constellation diagram comes in place. So it is a complex plane. So we have on the x-axis, we do have the real part, which is in phase, and on the y, it's the imaginary part, the quadrature component. And when we do look at this matrix now, with those 16 dots, so we scatter the symbols on this matrix with 16 dots, 4 by 4, we get a 16-QAM modulated signal. For reference, I also put the blue star there, which is actually just an on-off keying scheme, which you are using currently for your 10 gig LR transceivers. And it only has the in-phase component. There is no imaginary part in that in RZ, or even like for 100 gig transceivers, the same applies with PAM4 modulation. We do have 4 different states or 4 symbols, but only in the in-phase component, the real part. A different view in the constellation diagram, and it's going to be important then, is when we look at the phase itself and the amplitude. So we have 3 different states of the phase: the inner circle, the middle circle, and the outer circle. And combined with the phase itself, starting from 0 degrees, and we have a circle from 180 and minus 180. In total, we are 360 degrees. We can differentiate each symbol with amplitude and its phase. So it's a unique identifier, basically, for them. We're almost done with the theory part. Coming to signal-to-noise ratio. It is basically of our desired signal what we want to transmit, and the noise level we are having, the ratio what we measure. And the smaller that ratio is, the weaker the signal is, and it's more difficult for the receiver to detect the signal. It's quite similar like here, like in this audience now. If I'm speaking and you guys are really quiet, which you are, it's really easy to understand me. But if we would do the same now in a soccer stadium and everyone is cheering, the noise level would be very, very high, and it would be really hard for you guys to understand me and the same for me to talk. So we have a really good signal to noise ratio here now. Thank you very much. Why is this important? And you will see this now when we combine this about the constellation diagram with the signal to noise ratio, is how it will look like at the end of the day. So here we have a perfect constellation diagram, 16 clear spots, easy to identify by the receiver, because we have a signal to noise ratio of 30 dBs. But if the ratio gets worse, like 20 dBs, you see we scatter them more, and this, like the 5 dB, yeah, this is like yeah, it's kind of it's really hard to identify for the receiver which signal belongs to which matrix part, basically. Okay, you made it. This was the theory part, and now taking this theory in consideration how it looks on the CLI, and that's actually what we did. So we used DKIG's Nokia implementation with the SROS on their routers and switches, and plugged in a 400 gig QSFP-DD and looked actually on the operating system itself, just with the simple command, the show port command, what do we get back? And that's what I want to show you now and how we did it. So this is the show port, and there's nothing special. You should, yeah, you have seen this from your router and switch as well. Beside the fact, on the bottom, and I highlight them in green, we get now more details about a transceiver. So this is a coherent transceiver. We are talking about DWDM, and the great thing is it's a fully tunable coherent transceiver in the DWDM field from channel 13 up to channel 61. Here we go. Minimum frequency in megahertz, it's a pretty long number. Typically we do it in terahertz, it's 191.3 terahertz up to 169.1 terahertz. We are currently tunable to channel 23, and we got a couple of grids which we support. So grid 100 gigahertz and 50 gigahertz are well known, but we can also use 75 or 25 gigahertz and so on. So these are more the capability of the transceiver. Looking more in details now, diagnostic monitoring should be familiar so far, and I hope so. You have implemented in your network, like TX power, RX power, and temperature and voltage levels. I want to highlight the temperature part here. Why is the temperature so? In general, an optical transceiver takes power, converts it into light, but this is actually the small portion, and the bigger portion is heat. And therefore you have to monitor the heat pretty well, because thinking of such a tiny pluggable, doing 15 or even 17 watts in just one port, and you have 32 ports, you might end up with quite a lot of power consumption just on the transceiver side. And this will be exceeding 500 watts, and not taking into consideration CPU, RAM of your switch, and so on, and the other components. And first of all, the switch needs to supply that power, and the other thing is to get rid of the heat. So on one U, you could easily end up with 1 kilowatt of heat, and you have to get rid of that. So to monitor the temperature here as well is important, because also some switch manufacturers mentioned that some ports are able to provide that high power, those 15 or 17 watts feed in that port, and some ports are not capable to handle it, so they call them the high power ports. And yeah, you should get that out of the data sheet. Now coming to the coherent section, Nokia did this quite well. They did the entire coherent section when you run that show port command, and I'm gonna go through those steps now, or step by step basically. So let's start with the top one, present RX channel, and that's new. In the past, DWDM, you were able to tune the TX side, but the receiver side is typically, yeah, it's broadband, it takes basically everything. On a coherent transceiver, there is a need to change the RX channel. So our transmit side is on channel 23, what we saw previously, and also our receive channel is on channel 23, and we need to configure that the local oscillator inside of the coherent module can lock on that frequency to actually get our desired signal and get rid of the carrier. That is important. And yeah, that's need to be basically manual done. The next one is chromatic dispersion, and it has been around a little bit when you are operating CWDM networks in 10 gig, for example, but it wasn't, not a big issue so far. But for CWDM networks, especially at the L band, up to 1590, 1610 nanometers, there were some limits due to chromatic dispersion. So what is chromatic dispersion? Is while your light is traversing on the fiber, the velocity of the signal will change just due to the fact that it is on the fiber itself. And this might end up with some issues on the receiver side. So and that's called a chromatic dispersion. The coherent transceiver can compensate it with that DSP inside, with the digital signal processor. In here, we did a real-time measurement, oops, I made a mistake, of 220 picoseconds per nanometer. And this was a 15 kilometer span with a fiber having roughly 10 picoseconds per nanometer for chromatic dispersion. And we wondered ourselves as well, because we had, if you do the math, 10 by 15, you end up at 150 picoseconds per nanometer. So we did the counterpart test, made a back-to-back connectivity with 2 meters of jumper cable, and we ended up with a measurement of 80 picoseconds per nanometer. We're not quite sure where those 80 picoseconds were coming from, because actually they shouldn't be there. But then we got the diff and we knew, okay, the 220 picoseconds are quite helpful and all correct. And that's a really good way also, when you know the type of fiber you're running, you actually can do the math and figure out how long is your span just on the fact that you know the dispersion. So that's also a way to calculate the length of your span. The sweeping is straightforward. We do have also negative dispersion, that's also possible. And within that range, within those minus 25,000 picoseconds per nanometer up to 2,000 picoseconds per nanometer, our coherent transceiver is able to go through and compensate it basically, As we are having not only one polarization, we are also having 2 polarization directions, what I mentioned at the beginning with this 3D shape animation. There is a dispersion also there can happen a dispersion on the polarization velocity as well. So while this plane is traversing like this and the other one like this, they can differ as well. And this time difference is called the different group delay, and we do this measurement as well in picoseconds. And again, the transceiver can compensate it. You need to check the data sheet, but it's typically depending on, I'm going to show that later, which standard we're using, 10 picoseconds or up to 20 picoseconds we can compensate without any issue. Furthermore, we went over to the lower part, and there you see this RxQ margin. And this was quite interesting because we couldn't find any reference to the RxQ margin in the standards. And Nokia was there somehow creative. We've identified, okay, it's going to be the Q factor. So in the standards, people are talking about Q factor. Nokia is talking about a Q margin. What is it? Actually, it's the amount of our forward error correction. This is a part of the digital signal processor, how we can correct errors, how much gap or how much margin is there still left until the forward error correction is not capable to correct errors any longer. So here we still have 2.5 dB margin, which is pretty fine. So the FEC is working fine, and on this 15 kilometer span still. And if the span is, for example, just a back-to-back link, we had roughly 4 dB of margin for the forward error correction to still operate properly. And for sure, if you're going towards 0 dB, then the forward error correction won't be capable to correct errors any longer, and your bit rate, the post-FEC bit rate, so we here have the pre-FEC bit rate, the post-FEC bit rate will go up, and this will be seen on upper layers like layer 2 and layer 3 and so on, and your bandwidth will go down basically. And then also on the OSNR levels, as I mentioned at the beginning, like 30 dBs is a very good value to differentiate the different symbols in the constellation diagram. And here you see on both polarization, X and Y-X plane, 34 dB, which is pretty good. We are running very well there. And here, also it's important to check the data sheet of the transceiver itself, how much he is capable to compensate it. And OSNR tolerance is typically 24, 26 dB, and below that, it is difficult for the receiver to differentiate between the noise and the desired signal. Okay, and now the juicy part about coherent transceiver and the DSP actually inside is, it is not just a 400 gig transceiver. It is even more. You can configure that transceiver in a manner that you can break out 2 times 200 gig, or you want to run a link on 300 gig, or 4 times 100 gig. Just change the configuration, basically. That's the easy part, and in the DSP, different techniques will be changed, like a different forward error correction, or how he handles and treats the signal. Not every application mode, that's how they call it, are implemented either by the switch operating system or within the transceiver, and so therefore it's really important to be precise and check what is capable on both sides. And here we saw Nokia implemented some of the application codes, but we figured out as well that our transceiver we are using was only supporting 2 application modes, standardized by the OIF, the Optical Internet Forum. And interestingly, we actually set the compatibility to something totally different, but it was still working, but there are no checks in the operating system. So you have a compliance code, like the 400 gig ZR, but you set the compliance mode to OpenZR plus, and there is no check. So you need to know what you're doing there. To summarize this, there are standards behind it. There are two well-known standards. The one is the OIF 400 ZR, that's a little bit the older one. And the latest and newer one is the OpenZR Plus MSA. And please don't get confused about that ZR Plus, because that ZR, the Plus covers not only the Plus, it covers more. So yes, for sure, we have TX and RX power. They differ a little bit. We have a little bit of power budget there on the OIF side, roughly 6 dB. And on the OpenZR Plus MSA, they call it the 60 LA. The L is low power, and A is version A, I would say, but it was hard to identify where is the A coming from, because there's also a B, so I was assuming it's version A and B. It's less TX and RX power, but looking at the optical levels or optical tolerance levels like chromatic dispersion and polarization mode dispersion and the OSNR tolerance, there are differences. So in my understanding, the OpenZR Plus is more robust in terms of the dispersion components, and therefore I highlighted them, because you get actually up to 8 times more chromatic dispersion compensation or tolerance there actually. Even on the OSNR tolerance, you gain 2 dB more, which is not almost double, but a little bit less, and that's quite a lot on OSNR. Where is it coming from? OpenZR Plus defined a higher baud rate on the sampling, so they got a little bit above and using a different FEC, and this FEC is way more powerful compared to the one OIF uses. That's the major difference. And for you, when you implement transceivers or coherent transceivers, be aware that at the current stage they are not interoperable with each other. So OIF 400 ZR is not working with an OpenZR Plus MSA. You might change the configuration, then it's working, but it depends on the hardware, the DSP, if it's supporting both standards or just one. Yeah, this is my final slide, coming to the end of the presentation, and I'm happy to take questions if there are questions. And yeah, thank you very much.
Thank you, Thomas. Any questions for Thomas? Yes, Brian.
Yeah, Brian Candler, NSRC. You said that the receivers have to be set to a particular channel, tuned. Does that make any difference to the requirements for the optical multiplexers, or does that remove the need for doing filtering in the optical multiplexers?
General speaking, no, it doesn't change anything on the muxes. Yeah, I would say it like this.
Any other questions for Thomas? All right.
Okay.
Thank you very much.
Thank you.
So I think we'll finish off the session with Shishio-san talking to us about QoS traffic management challenge for AI and machine learning networks.
Thank you for introduction. My name is Schutzger, SE lead Alice Network. This is Bio, and my network engineer career is started in the 1997 at Ricoh Technosystems as a post-sales support engineer, and also I joined Cisco in the 2000 as a pre-sales engineer, and I supported the service provider network, and also I joined Arista since 2017. And next. Yeah, reason of this submission, I'm very exciting AI ML network future. But the reason why the might not understanding for the most of the network engineers and operators, because I submitted several AI ML network proposal, and but in the applicant 2024, but some submission was failed. And also I did presentation over on the January 15th, and the score of the presentation is very bad. So I feel the gap over my exciting and other people feeling. So I want to wrap up the past QoS challenge against next generation of application. This is the presentation target is onkochishin in Japanese. It means learning from past in English. So why QoS was needed before 2000? The difference of speed are quite high. Like LAN is 10 megabps, and also one is 128 kbps. The traditional router's default queuing mechanism is a FIFO, fast in, fast out. 1,500 byte packet takes 93.8 milliseconds on one, even though the 1.2 millisecond on LAN. 200 byte packet takes 12.5 millisecond on one, even though the 0.60 millisecond on LAN. But VoIP, voice over IP acceptable end-to-end latency is 150 millisecond. So queuing, the router priority is packet-based 3-bit IP precedence. It is TOS field. And VoIP RTP packet should transit as soon as possible. But TCP packet also need bandwidth to get good throughput. So operator find golden QoS rule by themselves evaluation. For example, NTT Communications provided a QoS service on their business services, and the CBWQ 19.2.90.1. And also I evaluation the other vendors router, And the golden rule was 5 million to 1. One big packet impact to the low latency packet due to the serialization delay. So to prevent this impact, link fragmentation for the long packet, 1050 byte divided by the 500, and interleaving fragment packet to the mission critical packet. The fragment packet reassembled the neighbor hop, and this technology was not needed by one speed evaluation. Ethernet deployed everywhere, even though the one networking. And also, we had used the frame relay services in business network at that time. Frame relay service also. Frame relay service has a network congestion notification mechanism, FECN and BECN. FECN means forwarding express congestion notification, and BECN is backward express congestion notification. Notify the congestion of the network to the subscriber. But as far as I know, the mechanism is not used because the TCP/IP automatically control traffic by sliding window mechanism. So better use bandwidth as possible as we can, then the ECN-based control, ECN-based traffic control. Around 2006, multimedia service started. So new mission critical application started. It is video. The packet sometimes bursty, and it uses a unicast and multicast, depend on the application. Different type of traffic compared with VoIP. VoIP and video use a different low latency queue. So we propose a 2 LLQ plus CBWQ, also multicast queue and unicast queue to avoid head-on line blocking. And also in this in the 2006, DS TOS field redefined by the DSCP. RFC 2474 is the different service field redefined TOS field, and DSCP for the multimedia services. And also RFC 5594 guideline for the diffserv class published other information. I explained later. This is a guideline of diffserv service classes. The telephony is fixed. This defines the service class name and the traffic characteristic, and the tolerance to the loss, delay, and jitter. Telephony is a fixed size small packet, constant emission rate in elastic and low rate flows. And also multimedia conference is a variable size packet, constant transit interval, and rate adaptation that reacted to loss. And real-time interactive RTP UDP stream interactive mostly variable rate. And business video is multimedia streaming, the variable size packet, and the elastic with variable rate, and broadcast video is the constant variable rate, and in elastic non-burst flows. And for the latency is very low, and jitter. And the jitter is This is the law. And what is data center QoS? Using BGP for routing in the large scale data center, it is IP cross network and Internet draft submit in the 2012. And it will be RS 7938 as the information in 2060. There is a variable type of service exist on the data center, but I asked one of the data center engineer, do you configure specific QoS on the data center? He answered, never configure the QoS. But I think the real answer is yes and no, because this is a data center switch QoS diagram. This is this architecture is Arista's data switch, but it is very similar with other equipment because we are using merchant silicon chip like a Broadcom. And ingress interface specify the trusted or untrusted host interface and polishing traffic in the ingress interface and use ACL to the assign DSCP or cost value to the packet and map DSCP cost to the traffic classes. And define traffic classes queuing map and there is a queuing map and apply the traffic shaping to the queue and perform per queue traffic scheduling and like a strict priority and weighted round robin. Based on the traffic class, rewrite cost and DSCP and shape traffic on the ingress interface. This is architecture of QoS. Default QoS behavior, input classification the trust cost on the layers port and trust DSCP on layers report. And traffic class mapping, automatically mapping cost DSCP to the traffic class. Traffic class mapping to the TXQ in our implementation. And queuing works level-based strict priority. And we have 8 unicast queue and 4 multicast queue assigned based traffic class. So QoS work without any explicit configuration for multi-services in data center. So how is the AI ML data center? In the AI ML data center, mostly the AI network traffic is a GPU to GPU. Typically, network packets are written to the kernel buffer and copied by the CPU to the application buffer. So CPU is a bottleneck. CPU is a major bottleneck, but RDMA, remote direct memory access, allows the application to bypass the OS network stack and the CPU processing and read-write directly from host memory or GPU memory on the other systems. RDMA over converged Ethernet, RoCE, was standard in the 2010, and RoCE V1 used a layered Ethernet frame limited to a single VLAN. But RoCE V2 introduced in the 2040 use on UDP IP encapsulation and it more commonly deployed. Feature of AI workload. Most of AI workload use collective communication for parallel computation. Collective communication allows information exchange across all the process of communicator. Commonly used collective communication primitive include broadcast, gather, scatter, all to all, global reduce, or all reduced, or and all together. Traffic pattern depend on the CCL model, a ring tree, and the version. Ultimate for improved performance because it is a kernel bypass. The prone to flow collision, microburst. Slowness member affect overlay the performance. AI training workload is high collaborative and sensitive to the job delay. This slide from the Alex Bujon and Meta, and she explained the importance of network I/O in the AI network. This explained the model and time spent in networking. Most of the model spending processing in the spend in networking. Model 2 is 57% using in network. So in this duration, expensive GPU sleeping during the time. So this is the traffic pattern. Tight time synchronization between the traffic flows and the little entropy. A small number of large size flows, 2 to 4 flow, panic, short periodic burst of the network activity flows by compute. CCL flip between the using ring and tree based on the GPU count and correction size. Network should be able to the effectively load balancing traffic flow and handle in incast, TCP incast. This is the network silicon for the AI network in today. XGS Tomahawk 4, this is the highest bandwidth. Scale out and high radius in for the spine, low latency box product, and the Tomahawk 4 support 6 by the 400 on the single chip, and also cloud-based cloud grade scale. Jericho 2C, it is a deep buffer and extensible for storage and Hadoop and routing network. Virtual output queuing, cell-based modular product. And it also released the fabric chip, Raman. So the combination and the Jericho chip and Raman chip, the maximum 60 slot, 460.8 terabps with a Raman fabric chip, like modular chassis. So non-blocking fabric. This is network design of AI network. One is AI leaf and spine. Oversubscription is 1-to-1 or greater FAT3. Require more the uplink than the total downlink. 1/1.2 or higher recommended consideration of the degree of ECMP dispersion and link failure. Various tuning of ECMP Q and as applicable. And the transfer cost between the leaf and the spine is high inter-switch link. And AI spine by the modular system. It is a very simple design, fabric and designed with N+1. And needed to consider the cabling designed based on the distance to the GPU node. Flow collision, ECMP trust distribution. Full distribution is not guaranteed in the high bandwidth, low flow count environment. A normal ECMP is based on the 5 tuple, Ethernet, IP, and UDP. Hash-based ECMP may cause the congestion because this is a low flow count. And the solution for the enhancement of ECMP on the AI network, like a dynamic load balancing, traffic load is considered and evenly distributed. Monitor the egress port data volume and queue. And also source interface-based ECMP, distributed based on the input port. And also custom UDP payload hashing, because Rocky 2 has a InfiniBand header to pair, so this custom UDP payload hashing is lead InfiniBand headers. And also cellular fabric system architecture, it is the AI spine network model. Input line card slice packet in input line card slice packet into cell. Cellular evenly spread across the fabrics for the very efficient load balancing. Fabric is over provisioning to the handle the failure. Packet reassemble and reassemble the final write as performed on the output line card. And the virtual output queuing mechanism is if ingress line card receive the packet, then the monitor credit over the output line card. If the credit is full, then the buffer in ingress. And VOQ mechanism is prevented head-on line blocking. And incast is Ncast N-to-1 communication. Congestion control is also needed for the TCP incast, where the traffic flow from multiple sources to a single port. Notify the source of congestion on the route to the control traffic by the CPU. Buffer management simplify the congestion control. For the notified control, to build a lossless network, PFC, priority flow control, defined IEEE 8021.1 QBB. It controls traffic by sending pause frame like a conventional .3x flow controller. PFC allows define the controllable traffic class by VLAN cost value for each application. And ECN, notify end-to-end using ECN bit, which is defined RFC 3168. ECN works with weighted random early detection, doublet. Queued and ECN are marked when the available queue size in the between the maximum and the minimum threshold. So does technology enough for AI network to no. It looks a patchwork for the traditional QoS and the load balancing technology. The traffic pattern sometimes changed by the version and the type of CCL. We have not find the golden pattern of the QoS for the PFC and the ECN for TCP incast. Should consider new load balancing mechanism algorithm for the flow collision, which low latency, low jitter, lossless and bursty traffic. It is not automatically or fine default setting against the GPU to GPU traffic. So to support next generation open AI network infrastructure, Ultra Ethernet was established. It is open interconnected high performance, expanded the Ethernet to the meet AI requirement. And UEC defines these standard technology, multipath and packet spraying, and flexible delivery orders, modern congestion mitigation mechanism, end-to-end latency, and large scale 1 million endpoint, stable and reliable. This is conclusion. Learning from past, VoIP traffic, multi-cat video traffic, and data center default QoS setting. Traffic management for AI network, it is required PFC, ECN, and the cell-based VO virtual output queuing architecture interfaces. And new ECMP approach, DLB source interface-based ECMP, and the custom payload for the InfiniBand headers. The Ultra Ethernet provides new traffic management, QoS, visibility for the AI networking. And the more detailed AI infrastructure technology will explain in tomorrow's tutorial session. This is tomorrow's tutorial session. This is reference for AI network. My presentation ended. Thank you for attending.
Thank you, Shishio. Any questions for Shishio? So we've got time on the clock. Yes.
Hello, just reading a question from the chat. If you could please ask. In an MPLS VPN v4 network using P and PE as Arista router, can we do bandwidth reservation per VRF on MPLS core without rewriting the customer's DSCP value? DSCP value.
Yeah. We can automatically mapping to the DSCP to traffic classing. So it is depend on the DSCP value.
Okay. Any other questions? All right. If that's it, thank you so much, Shishio. And I think we can come to the end of this session, which brings us straight into the 1 o'clock lunch. Thank you very much, and we'll see you all at 2:30.